The question that I have here is, could you do an example on friction involving a flat belt? You know what, let's go ahead and do a couple of small but different problems. So here's my first problem. We have a cylinder that is being held against a wall with the help of a belt, like shown over here. The weight of the cylinder is 20 pounds and this angle is 45 degrees. Coefficient of friction between the belt and the cylinder is 0.4. It's further given that the slipping does not occur at point A, that is between the wall and the cylinder. Question is to determine the minimum value of F so that the belt does not slip over the cylinder. So in this picture, I went ahead and marked a few other geometrical details that will help us solve this problem. This line right here is a radius that is perpendicular to this part of the belt. Remember, the belt will always be tangent to the circle, right? Connecting this point to the center of the circle, we see that this triangle and this triangle are congruent, right? And therefore, this angle is 22.5 degrees, in other words, half of this, right? And this is 67.5, this is 67.5, and therefore this works out to be 45 degrees. Expressing that in radians, we get this angle right here to be pi over 4. And therefore this pi over 4 is the contact angle for this contact right here between the belt and the cylinder. Let's also recall the general friction equation we have derived in one of the previous videos for a system involving a roller and a belt. In this equation, T1 is greater than T2 and mu is the coefficient of friction, alpha is the contact angle, right? Before we can apply this equation properly, we want to understand the mechanism here. Namely, we want to understand the impending motion. So, since there is no slip at point A, which is given to us, right? If the cylinder is to slip on the belt, it's going to slip in the clockwise direction. In other words, there is going to be a relative impending motion on the belt, like shown over here. In other words, relative to the cylinder, belt is going to be moving in that direction, vertically upward direction. Since T is equal to F plus the frictional force, T is greater than F. T is greater than F. And this allows us to apply this equation properly for the system here. So here is the equation. T has to go on the left side because the exponential term is greater than 1. Mu is 0.4, contact angle is pi over 4. So we get this relationship for T. We have two unknowns, T and F, and therefore we need one more equation to solve. We can write down a moment equilibrium equation about point A for the forces acting on the cylinder. Summing up the moments about point A in the counterclockwise direction, moment of tension T right here is T multiplied by this distance, and that distance is equal to R plus this part right there, which is R cosine 45, right? So we have this, and that goes in as a positive term in that equation because the moment associated with this T is a counterclockwise moment. The arm length for W is simply R, and the arm length for F is 2 times R. And these two forces give us clockwise moments. So they go in as negative terms in that equation. So we have two equations, two unknowns, and solving the two equations simultaneously, we get a value of 59.4 pounds for F. This is the minimum force that we need to apply on the belt in order to hold the cylinder in equilibrium. We know that this force is proportional to W, right? And therefore, for example, if I were to double the weight, the value of the force needed to hold the cylinder is going to be double 2. From a physical, intuitive point of view, this makes sense, right? Here's a problem number 2, another fairly common problem in this category. We have a cord that goes around this fixed supporting cylinder. The cord is attached to a weight of 300 pounds on one side. The cord makes a contact of 2.5 turns on the cylinder. The question is, what is the largest P that can be applied on the cord before the cord slips on the supporting rod? Let's keep the general friction equation for a roller cord system here. We know that if we pull on the cord with the large enough force, the cord is going to be moving vertically down, and therefore this is the impending motion of the cord, right? The frictional force on the cord is going to be resisting this impending motion, and therefore the direction of the frictional force on the cord is going to be this one right there, the one shown by the green arrow. This tells us that P consists of both the frictional force and the weight W, and therefore P is greater than W. Now applying this general friction equation, we have this. This is the relationship between P and W. P goes on the left side. We have 2.5 turns of cord on the cylinder, and therefore the contact angle between the cord and the cylinder is 2.5 times 2 pi, which is 5 pi. The coefficient of friction is 0.3, and then along with the contact angle, we get this value for P. P is 33,315.6 pounds. That is, the cord is going to slip on the cylinder when P is greater than 33,315.6 pounds. Now to answer the question, the largest force that can be applied on the cord before the cord slips on the supporting rod is this, 33,315.6 pounds. Now you might wonder, note the huge difference between the weight, which is only 300 pounds, and the force that needs to be applied on the cord in order to make the cord slip on the cylinder. So 2.5 turns makes a huge difference. This is our third problem. This is a classic problem involving a motor and a wheel which may be connected to, let's say, a conveyor belt. The flat belt here goes around pulley 1, which is attached to motor 1, and the wheel. The geometry and the values of the coefficient of friction are given. The allowable tension of the belt is 1200 Newton. The question is to determine the maximum torque that can be applied on the wheel before slippage occurs between the belt and the pulleys. Let's keep a general friction equation here. Let's first find out if slipping is to occur, whether it's going to occur on pulley 1 or pulley 2 first. I have drawn some lines here that should help us find the contact angle for the two pulleys. It's easy to see that this triangle and this triangle are congruent. This angle is given as 60 degrees, and therefore each of these must be 60 degrees. The contact angle alpha 2 on pulley 2 is 180 degrees plus 60, which is 4/3 pi. If this angle is 60 degrees, this angle, this little angle right here, is 30 degrees, right? And therefore, the contact angle on pulley number 1, alpha 1, is 360 degrees minus 90 over here, minus another 90, minus 30 times 2, right? Alpha 1 works out to be 2/3 pi. Let's assume that the motor here turns in the clockwise direction. When it does, it's going to apply a frictional force in the clockwise direction indicated by the green arrow on pulley 1. T1 therefore equals to T2 plus the frictional force, and therefore T1 is greater than T2, right? So on this basis, we place T1 on the left side as the friction equation. So this is the relationship between T1 and T2. It's given that the allowable tension on the belt is 1200 Newton, and therefore equating T1 to 1200 Newton, we get a value of 789.5 Newton for T2. In a similar manner, applying the friction equation to pulley number 2, we get a value of 519.5 Newton for T2. So to summarize, to prevent slippage on pulley number 1, T2 should not be less than 789.5 Newton. To prevent slippage on pulley number 2, T2 should not be less than 519.5. And therefore, to prevent slippage on either pulley, T2 should not be less than 789.5 Newton. So this is the minimum value of T2. Summarizing these values one more time here, the minimum value of T2 is 789.5 Newton. The maximum value of T1, which is the allowable tension of the belt, is 1200 Newton. Therefore, the maximum torque that can be applied on pulley number 2, which is the wheel, right, is given by this equation right here. The torque due to T1 is T1 multiplied by the radius. Torque due to T2 is T2 multiplied by the radius. T1 times the radius is a clockwise torque, but T2 times the radius is a counterclockwise torque. So the T1 times the radius goes in as a positive term here. T2 times the radius goes in as a negative term. So to answer the question for this problem, the maximum torque that can be applied on pulley number 2 before slippage occurs on either pulley is 123.15 Newton meter.